Hey everyone, in this video we're going to be estimating a population mean. So our first objective is to obtain a point estimate for the population mean. And a point estimate is just the value of a statistic that estimates the value of a parameter. We did this previously with the population proportion. So for example, sample mean, x bar, is just a point estimate of the population mean, mu. So here's our first example. The website fueleconomy.gov allows drivers to report the miles per gallon of their vehicle. The data in this table show the reported miles per gallon for 2014 Toyota Camry automobiles for 16 different owners. Obtain a point estimate of the population mean miles per gallon of this car. Okay, so here's our sample mean. Just add up all the values and divide by the number that there were, 16. Then we get 28.1 miles per gallon. And so the point estimate of the mean, mu, is 28.1 miles per gallon. And so remember, round statistics to one more decimal point than the raw data if necessary. And so next, let's state properties of students' t-distribution. So students' t-distribution, first of all, students is the name of a person. It's actually a pseudonym. It's a different distribution, and we've been working with standard normal distribution. Another way to say that is your z distribution. So now we're introducing this new letter t, but think of it very similar to you think of as z. So suppose a simple random sample of size n is taken from a population that follows a normal distribution. The distribution of t, which here's how you compute t. Notice that it looks really similar to your computation for z, but we're using s now this time, which is your sample standard deviation. So it's your x bar, your statistic, minus your mean mu from your population, over your sample standard deviation divided by square root of n. So the distribution of t follows students' t distribution with n minus 1 degrees of freedom. Real quick, a note on degrees of freedom, just a way to think about that to help you. If you think about, like, let's say there's 5 students and there was 5 markers on the whiteboard and the students had to each pick one. The first 4 students had freedom to choose, but the 5th student is left with no freedom to choose because there's only one marker left. So that's the idea of degrees of freedom. So n minus 1 degrees of freedom is just one number less than your sample size. And this is where x bar is our sample mean and s is our sample standard deviation. So why we work with t distribution now instead of z distribution, just so you know where this came from, this comes from not knowing the population standard deviation. So that's the difference here. We don't know sigma, and so we're going to use s to estimate it. And so let's use some software to obtain 2,000 samples, randomly sampled, of size 5 from a normal population. We actually know that the mean mu is 50 and the standard deviation is 10. We're going to calculate the sample mean and the sample standard deviation for each sample. And then we're going to compute z and t for each sample. So notice the difference in these formulas. It's very subtle, but the difference is the standard deviation. For z, we use the population standard deviation, sigma. For t, we're using the sample standard deviation. And then we're going to draw histograms for both. So let's go ahead and go over to StatCrunch and work this out. Okay, so here's our result, but let me show you how I got this. So I'm going to get rid of all this. First, we have to simulate our data. So let's do that. Okay, so what I'm going to do is I'm going to go to Data, Simulate Normal, and we want 2,000 samples of size 5. And then we know our mean was 50 and our standard deviation was 10. Okay, and let's just go down here. I'm going to go ahead and round and hit compute. Okay, so there's our 2,000 samples. If we scrolled, there'd be 2,000 rows. So now to compute z, we're pretty much ready, but let me show you what we need for that real quick. So for Z, we need our sample mean, so we do need to compute that, but then we're going to subtract 50 for our population mean and divide by 10, which is our standard deviation from the population, over square root of our sample size 5. Okay, so I need to still compute X bar for each of these samples, each of these rows. So let's do that real quick. So we need the mean for each of our 2,000 samples. So we're going to go to Summary Stats, Rows, and we want for each of these columns just the mean. Okay, we're going to store this in our table. And so there's our sample mean for each of our 2,000 samples. Okay, now the way we're going to do that computation is we actually have to enter it in as a expression. So we're going to go to Data, Compute, Expression. And we have to type this in. Okay, so I'm going to build this equation. So let me show you again what it looks like. It's going to be our sample mean minus 50 divided by 10 over square root 5. So that's what I'm typing in. Okay, so I'm going to put parentheses. Our sample mean is in our row mean. So we computed that. So I can relabel it X bar if that's easier for you. But that's what this is. So I say add that. And we need to subtract 50. Okay, and then we're going to divide. Actually, let's delete that real quick. It needs to be outside the parentheses. So click out here, divide, and I'm going to put parentheses, 10 divided by, and I'm going to go over here to functions and scroll down to S for square root, right here, square root, function, and we want square root of 5. Okay, so notice what this is. This is X bar minus 50 over 10 over square root 5. We're going to say, okay, and I'm going to label this as Z and compute. All right, so there's Z. Okay, there's our Z scores for each of our 2,000 samples. Now, in order to do this for T, remember the difference is with T, we don't know the standard deviation. Let's say we didn't know that the population standard deviation was 10. What we have to do is we have to compute that. So I need to do another computation first. I'm going to go to Stat, Summary Stat, Rows, and what I want is a standard deviation for each of my 5 rows here. Okay, and so I'm going to go down here to standard deviation. Let's go ahead and store that in our table and hit compute. Okay, so that's our sample standard deviation. Notice it changes depending on each sample. For our population, it was 10, but for our samples, it's 12, it's 8, 7, 10, 12, and so on. Okay, so now let's compute T. It's really similar to what we did for Z. So I'm going to say data, compute, expression. And the nice thing is it stored that for me. Okay, so I'm going to just edit it. And it's no longer 10 for my standard deviation, so I'm going to erase that. And I need to input the row standard deviation. This is the same as S from our formula. So I'm going to insert that. And so this is saying X bar minus 50 divided by S divided by square root 5. Okay, and I'm going to call this T. And there it is. So there's our T values or T scores. Okay, and then let's just graph them. So graph, histogram, let's do each one. So we want Z. Okay, and I'm going to go ahead and do relative frequency. And I'm just going to do 0.2 for the width, just so you can see it. And I think that's good. Okay, compute. Okay, and this is our histogram for Z. This is our Z distribution. Notice it's relatively normal looking. Okay, all right, let's do the same thing for T. So I'm going to go to graph, histogram. Now, I'm going to go down here to T. And let's go ahead and do relative frequency again. This time, because I've already seen the data, I played with the width. I'm going to pick 0.5. And that should be good. Okay, compute. And there is our t-distribution. Okay, so that's how we do this in StatCrunch. A lot of steps, but it's a lot better than having to do 2,000 samples and computations by hand. Okay, so here's our histograms that we just looked at for sample size 5 for Z and T. And so notice that the histogram in figure A, the one for Z, it's symmetric and bell-shaped for the most part, and then it's centered at 0. Virtually all the rectangles lying between -3 and 3. So another way to think about that is that Z, with our sample size of 5, follows a standard normal distribution. The other histogram for T, same sample size, it's also symmetric and bell-shaped, centered at 0, but the histogram of T has longer tails. That is, it's more dispersed. So it's unlikely that T follows a standard normal distribution. This additional spread is due to the fact that we divide by the sample standard deviation over square root n to find T instead of the population standard deviation over square root n. So we're going to do this again. We won't go through the process, but for sample size of 10, and then you would get these histograms. So notice you have your Z distribution, and then over here your T distribution for sample size 10. Okay, so the one for Z is symmetric, bell-shaped, centered at 0, and most of the rectangles lie between -3 and 3. And so again, this Z distribution follows a standard normal distribution. For our T distribution, it's also symmetric, bell-shaped, and centered at 0, but again, it has longer tails. It's more dispersed than Z was. So T, still with a new sample size, seems to not follow a standard normal distribution. And so an important distinction is that the distribution of T with sample size 10 is actually less dispersed than our first one when our sample size was 5. So we conclude that there are different T distributions for different sample sizes. And so in addition, the spread of the distribution of T actually decreases as the sample size increases. It can be shown that as sample size n increases, the distribution of T behaves more and more like the standard normal distribution. So this is good to know. If we keep increasing our sample size, then T is approximately normally distributed like Z is. And remember, we are just using T because this is good for situations where we don't necessarily know the population standard deviation. And so properties of the T distribution. Number 1, it's different for different degrees of freedom. Number 2, it's centered at 0 and symmetric about 0. Number 3, the area under the curve is 1. The area under the curve to the right of 0 equals the area under the curve to the left of 0, which is 1/2. These are things we've seen in the past. And then number 4, as T increases or decreases without bound, the graph approaches but never really equals 0. Number 5, the area in the tails of our T distribution is a little greater than the area in the tails of the standard normal distribution. So this is the first main difference that we're saying from our standard normal distribution. And this is because we're using our sample standard deviation as an estimate for our population standard deviation. And when we do this, we actually introduce variability into this statistic. Number 6, as the sample size n increases, the density curve of T gets closer to the standard normal density curve. This result occurs because, as our sample size increases, the value of our sample standard deviation actually gets closer to our population standard deviation. This is by the law of large numbers. Okay, so here's a figure for our T distribution for sample sizes 5 and 15, along with the standard normal density curve. So blue is the normal curve, and then it's a little hard to tell, but if you think of it like the shortest one, that's with the smaller sample size 5. This one that's getting closer to the normal curve, That's with a higher sample size. So if we increase the sample size even more, it would approximate the blue curve even better. So next, let's determine t-values. Now that we learned a little bit about what t-distribution is. So the notation z sub alpha is used to represent the z-score, whose area under the normal curve to the right of z sub alpha is alpha. We've talked about that in the past, and just reminding you of that because it's going to be similar for t sub alpha. This is going to be the t-value, whose area under the t-distribution curve is to the right of this number t sub alpha, and that area value is whatever number alpha is. So for example, find the t-value such that the area under the t-distribution to the right of this t-value is 0.10. Assuming 15 degrees of freedom, that is t sub 0.10 with 15 degrees of freedom. So again, this number here, this is where we're working with the area. We actually are told the area is 0.10, and we are looking for the corresponding t-value, the t number. Okay, so our figure here shows what we're talking about. The unknown value of t is what we want. We know the area already. This area under the curve is 0.10. And so you can use tables for this or technology. So we have a table here, and what you would do is you would look for two things. You're going to look on the rows for your degrees of freedom that's told to you. In this case, it's 15. And then in the columns for the area. And when you look at this table, which you can find online or in a textbook, you're going to match those up, and you'll find that the t-value is 1.341. Okay? And so when t equals 1.341, we know that, and there's 15 degrees of freedom, the area under the curve to the right of this value is 0.10. So the critical value of z with an area to the right of 0.10 is approximately 1.28, which is actually smaller than the critical value of t with 15 degrees of freedom. Now this is because the t-distribution has more spread than the z-distribution. So this statement's just to compare t with z. Our t-value we just found from our table, and notice our z-value, which we could also find from a table, it's smaller. So next, let's construct and interpret a confidence interval for the population mean. Okay, so constructing a 1 minus alpha times 100% confidence interval for mu. Provided that a sample data comes from a simple random sample or randomized experiment, the sample size is small relative to the population size. So remember that we want the sample size to be 5% or less of our population size, and that the data come from a population that is normally distributed, or that the sample size is large. So if all that's true, so remember we have to check these things. If these three things are true, then our sample data is approximately normally distributed. And so then a confidence interval for our mean mu is given by a lower bound and an upper bound. Okay, so we've seen this idea before. Let me just kind of go into a little bit of details again. In this case, the main difference is our values in our calculation. So remember, we have our margin of error that we add and subtract from our mean here. So in this case, we're using our sample mean, x bar, and in this one, for the lower bound, we're subtracting this margin of error. For the upper bound, it's your sample mean plus the margin of error. And so the main difference now is that we're using t instead of z, and this is still our standard deviation calculation, but we're using our sample standard deviation instead of sigma from the population. So again, we've seen this in the past. It's just that what's new is s and t. And then t sub alpha over 2 is the critical value with n minus 1 degrees of freedom. And so because this confidence interval uses t distribution, we often call it the t interval. And then the margin of error for constructing confidence intervals about the population mean is this computation here. So your t value times your standard deviation over here. technically the standard deviation of the sample over the square root of the sample size. And so we have what's called the normality condition. And so Gossett is the person who is credited for developing the t-distribution. Earlier when we learned about it, it said students t-distribution. That was his pseudonym that he used. And so when Gossett developed the t-distribution, he assumed the sample data came from a population that is normally distributed. Most distributions are not exactly normally distributed, so that's why we actually have to do this whole verifying our sample data to make sure it appears normal enough before using the t-distribution to construct the confidence intervals for the population mean. Okay, so we have a couple of options. Option 1 to do this verification is that if n is less than 30. So if our sample size is less than 30, we can draw a normal probability plot to check that the normality condition and a box plot to check for outliers. If the data appear to come from a population that is approximately normal with no outliers, then it's reasonable to use students' t-distribution to construct a confidence interval for a population mean. So our checking that we have to do here is if our sample size is less than 30, we check these two things, our normal probability plot and our box plot. And we look for approximately normal distribution. The other option, this one's a little different, it relies on the robustness of constructing confidence intervals using students' t-distribution. So an inferential method is considered robust if it's accurate despite minor departures from its underlying assumptions. And so we have some cases here. If your sample size is less than 15, you use the student's t-distribution to construct a confidence intervals about a population mean if the sample data are symmetric with no outliers. The data should not be skewed left or right. This condition may be verified with a box plot. The median should be in the middle of the box, and the whiskers should be of equal length. If your sample size is between 15 and 30, you're going to use students' t-distribution to construct your confidence intervals about your population mean, provided the sample data do not have extreme skewness and no outliers. And then if n is greater than or equal to 30, use students' t-distribution to construct confidence intervals about a population mean, even for skewed distributions. And that's because this relies on a couple of things we learned previously. The central limit theorem, which is for the distribution of the sample mean to be approximately normal, and the law of large numbers, which says that the sample standard deviation is close to the population standard deviation. Okay, so we're going to try this out. I know it's kind of a lot, but let's see if this makes sense using this example. So the website fueleconomy.gov allows drivers to report the miles per gallon of their vehicle. So this table here shows the reported miles per gallon for a 2014 Toyota Camry for 16 different owners. We're going to treat this sample as random, and then we're going to construct a 95% confidence interval for the mean miles per gallon, and then interpret the interval. Okay, so we got to do some checking first. So the first thing is to see if the data is random, and in this case it is. We can pretty much assume that it was a random sample of 16 people out of all the 2014 Camry owners. And then also, it's likely that more than 16, way more than 16 people own that car. So the sample size is small. It's less than 5% of the population size. And then so here is our normal probability plot and the box plot from our table. And so then we have our correlation coefficient, which is going to be 0.954. I'm going to show you how to do this again in StatCrunch. We've done this in the past, but before we do that real quick, let's go over here. So we've talked about this previously, but if our correlation coefficient is greater than our critical value, which I'm going to show you that it is because we'll get this number from the table, then what we could say is that the sample data come from a population that's normally distributed. So this is all things that we've talked about previously. We're kind of putting a lot of stuff together that we've seen before. And then their box plot doesn't reveal any outliers. And so the requirements for constructing the confidence interval are satisfied using option 1. So let's go ahead and go over to StatCrunch real quick and just construct those things. Okay, so what I've done is I've inputted the raw data from our table. This is the miles per gallon. And what we're going to do first is get our probability plot here. We're going to go to graph, QQ plot. Okay, so I'm going to select my column. And we're going to add the correlation coefficient. And let's add the normal quantiles on the y-axis. That should be good. Compute. And there we have it. Okay, so notice what we have here at the top. The correlation coefficient was calculated for us. That's where that 0.954 came from on our information that we looked at. So we want to do that, and then we also want to do a box plot. So we're going to go to graph, box plot, and we want our variable 1. And let's see, we're going to go ahead and draw our boxes horizontally. And we've already had the fences there, and that looks good. Okay, compute, and there's our box plot. Okay, so that's how we would get those things using StatCrunch. And then now that we have our correlation coefficient calculated, we can go over to our critical value table. Let's see, and here I have it. And we want to verify based on our sample size, which was 16, that our correlation coefficient was greater, which it is. It's greater than the 0.941. If you did decide to use option 2 to make sure that these requirements were satisfied, the box plot suggests the distribution of the sample data is skewed right. That's because if you look at it, the median is actually to the left of the center of the box, but there's no outliers. And so because the sample size is 16 and the skewness is not extreme, the requirement for constructing the confidence interval using option 2 is satisfied. Okay, so now that we did that verification, we can move forward, and we're going to we determined that the sample mean in a previous example is 28.1 miles per gallon, and then we can calculate our standard deviation for the sample to be 2.38 miles per gallon. And so for 95% confidence interval, alpha is 1 minus the 0.95. So it's 0.05 for alpha. Our sample size is 16. And so we want to find t sub 0.025 based on, we got that from plugging in alpha over 2 right here. And then our degrees of freedom, and remember, is n minus 1. So that's where 15 comes from. And then we go to our table for t distribution, and we find that the corresponding value for this area to the right of this t number. So remember, the table tells us that 0.025 is the area to the right of this t number. So the corresponding t value based on 15 degrees of freedom in this area is 2.131. And so then we still need to get our upper and lower bounds for our confidence interval. So here's our formula for the lower bound. Our sample mean minus our t value here times our standard deviation from our sample over square root of the sample size. So just plugging in a bunch of things. So we plug in our sample mean, our t value, standard deviation, sample size. We get 26.83 for our lower bound. Very similar, but with a plus sign for the upper bound, we get 29.31. And so we can say we're 95% confident that the mean miles per gallon of all 2014 Toyota Camry cars is between 26.83 and 29.37 miles per gallon. Okay, so just one more quick note on using technology. If you use Minitab, you will get your statistics here. And then notice how the lower and upper bounds are mentioned. It's just in the interval, so it's saying your lower bound is this first value, upper bound is the second value here. And so we would come to the same conclusion. So what should we do if the requirements to compute a t interval are not met? So we just verified an example where they were. So if they were not met. So what we could do is increase the sample size beyond 30 observations, or we could try to use non-parametric procedures. Non-parametric procedures typically don't require normality, and the methods are resistant to outliers. And another option is to use resampling methods, such as a method called bootstrapping, which we may get to later. All right, so most of our examples, though, we're going to be able to satisfy those conditions and use our t-distribution. So next, we're going to determine the sample size needed to estimate population mean within a specified margin of error. So we've done this in a previous topic with the population proportion, but pretty much notice what you're looking for now. You're looking for n. You're looking for your sample size based on a margin of error you're trying to stay within. And so determining your sample size n, the sample size required to estimate the population mean, mu, with a certain level of confidence and a specified margin of error, e, is given by this formula. Then we round to the nearest whole number. So we did something similar to this with the population proportion previously. So it's just a matter of plugging in. If you know z, and you know your sample standard deviation, and you know your margin of error that you're working with, you plug those values in, and you're going to get n, your sample size. So let's consider that same example with the 2014 Camrys. How large a sample is required to estimate the mean miles per gallon within 0.5 miles per gallon with 95% confidence? Okay, so we have everything we need. We're just plugging in. And so notice this time we are using a z-score. So for 95% confidence, alpha is 0.05. We plug that in here. We get z sub 0.025. We go to our standard normal distribution table. That's where this 1.96 comes from. And then we have S that we've calculated already, our standard deviation. We know what the margin of error should be based on what we're told. We just plug all that in, square it, and our sample size, if we round up, is 88. So a sample size of 88 results in an interval estimate of the population mean, miles per gallon, of 2014 Toyota Camry with a margin of error of 0.5 miles per gallon with 95% confidence. All right, so we did it. That's it for this one. Thanks for watching.